Record. So what we're going to talk about today is piecewise regression in spline modeling. And this stuff is really cool and really useful. And I've developed these slides over a number of years and have some, different data sets that I talk about with it. So, I'm sure a lot of you are familiar with spline modeling and using, smoothing splines to create a kind of a really flexible function to model some kind of mean response over time, possibly, or it could be over with respect to another predictor. And so we'll talk about that, but I want to start like at the very basic level of how we create, changes in the trajectory of a function. And the simplest example or the simplest form would be where you just have one change point. So you have some sort of function, you can think of it as a straight line, and maybe you want it to change directions. And how you do that, because that's really the foundation of spline modeling. And so we start off talking about piecewise regression, where you have some different regression lines and you're joining them together. Okay, so there's a lot of material you can refer to in the course notes, and then these slides are pretty thorough as well. So, I'm sure you guys have heard of the, parametric, semi-parametric, and non-parametric. You've heard of those terms before. Parametric function is completely specified, has a number of parameters in it and a function that's well defined. A non-parametric function is something that's either not easily expressed as a compact function or can't be at all. And the goal of like non-parametric regression then is to offer like a really flexible function that doesn't have any constraints. It's not constrained to be linear, quadratic, cubic, or anything like that, but it's just modeling the data as it is. So on one end, you have the parametric functions, that's the most constrained, and non-parametric is the least constrained. And then in between, there's some modeling that you can do that has a little bit of both, which is a semi-parametric modeling. Okay, so today we're really talking about the semi-parametric, non-parametric regression functions. So really, the thing is, piecewise polynomial regression and even spline modeling technically is parametric, but it was that first part of what I talked about, something that's really complicated to express. You can express it as a parametric function, so technically it is, but really it's often considered non-parametric once we get a lot of knots in the model and a lot of different things that we're joining together. Okay, so depends on how you consider the words that you use. So like I mentioned, piecewise polynomial regression offers a researcher a more flexible way to model a mean function over time, or whatever predictor you're considering. And the pieces are joined together so the function is continuous. If we do that, then it's spline modeling. But if there may be hard changes at a certain point, it could be continuous but not differentiable. Then we just call it piecewise polynomial regression. So I would think that piecewise polynomial regression is kind of the more general term. Spline modeling is the subset of that we're involving smooth functions over time. So the question is, how do we go about this, and when do we use this type of modeling? Well, just to start at the real basic level, like I talked about, consider some health outcome that we're measuring, and we'll say it's a function of exposure to an environmental risk factor. So this could be like air pollution, something like that, that as that increases, as that environmental risk factor increases, that is leading to a higher health risk. But it could be that, like at lower levels, like again, if you're thinking like air pollution or something like that, or exposure they have to contaminants in the air, where they're working, possibly if we're considering those kind of subjects. Maybe they're working in a plant where there's dust in the air or something like that. But at low levels, maybe there's no health response, and you have to reach a certain point where it becomes an issue. And so, this is just a simple diagram showing like their health stays well, up to a certain point, but once the exposure level gets to a certain point, then there really is a stronger dose-response relationship, or maybe it could even be something like this where there's no, like it could be flat. That's not flat, but you know what I'm trying to do there. Just imagine that as a flat function. And then after that point, it drops off, right? So it could be like this one I have over here is just a little bit of a drop, but maybe there's no relationship. There's no dose-response relationship. And at a certain point, then there is one. So how do we model that? We have to join two regression lines together. And it's actually really easy to do. What you do, X is your, whatever that exposure is. It could be, some type of localized air pollution. And then you create another variable, and K is where that point is, where that value of X is, where there's a change. So we call that the knot. And you can create a variable that's the max of X minus K. So K is some constant, and X is a variable. And so you can easily create that new variable, the max of X minus K and 0. And so what's going to happen is for X less than K, this piece doesn't kick in, right? Because the max is going to be 0. But once X reaches K and goes above it, then this piece is going to kick in. So you can actually write this function here that I have here. You can break it down into two pieces. For X less than K, this is what it looks like. It's just a simple linear regression. And then for X greater than or equal to K, you can express it this way. It's also a simple line. And the slope of the original line is beta 1, and the slope of the line after point K is beta 1 plus beta 2. So beta 2 is the change. And that's the thing that we're going to usually want to test is there a point where that dose-response relationship changes? And beta 2 is going to be the thing that expresses that. But because we have a new line, we have a new intercept. So if you draw this out, if we have, say we have a line coming down here, it's a little steeper than I wanted it, and it disappeared. I didn't want it. So if we have a line like this, and it's going to disappear on me again. Okay, let's see if that one stays. And then let's say our knot's here. Well, if we have a new line at this point and say that that changes directions, and let's say in this case it goes up. So let's say our line goes like this at that point. The slope of this line is beta 1. Here's our beta 1. And then this slope is beta 1 plus beta 2. But the intercept, even though we don't see it, the intercept for that line would be, so I'm going to use a dashed line. This is beta naught prime right there, right? And this is our beta naught here. So we don't actually use, we don't see it because we see the solid part, but we have a way to anchor that new regression line in. And we really, what we see is the change in the slopes when we put those two together. Okay. So here's an example with real data, and this kind of, I was kind of alluding to this data. We've done at National Jewish, we've done a lot of work with people that have worked in beryllium metal plants. So they're using beryllium metal to construct things, and Rocky Flats was a company that kind of in the northwest side of town that used to they were constructing actually nuclear weapons there, and it involved using beryllium metal. And so this plant has been closed for many years, and obviously there's a lot of concern about it. Is there concern about radiation in the area and so forth? So obviously they did a lot of testing, and as they've developed new communities there and housing, they've had to do a lot of testing to make sure the area is okay. But that's a local company that was actually using beryllium metal in the manufacturing of their products. There's other beryllium metal plants, and they may be constructing other things. So different places across the United States, they use beryllium metal. But what they found is that this metal, when they were cutting it and it creating beryllium dust, workers would actually breathe it in, and they would develop, some of them would develop chronic beryllium disease. They had to name it because it was specific to that metal that they were breathing. Some of the people would develop this disease, and others wouldn't. Some would become sensitized to it and not progress, but then others would initially get beryllium sensitization, and then they'd progress into CBD. And we observed that those that progressed to CBD their progression would speed up in their health outcomes. So one of the outcomes we're considering here, we looked at many, but one of them was the alveolar arterial oxygen tension difference at rest, higher values indicating worse health. So I'm going to build a model to look at this outcome, and here are the predictors that we're going to consider. Time, CBDX is the time when subjects progressed from BES to CBD, if they did. Progression group is a class variable, 0, 1, or 2. So it would be 0 if they progressed before we observed them, before they came into National Jewish. 1 if they progressed during observation, and 2 if they progressed afterwards, or maybe they never progressed. And then stage is a stage of illness. Either they're just sensitized or they have CBD. And why is their outcome is described. So here's our model, and I'm going to use a spline model in this case. So once they progress, I'm going to use a hard change point, and their dose-response relationship, we're going to assume is different than when they were just sensitized. Or this would be a way to actually test if they change in their dose-response relationship. So we're looking, again, X here is time and Y is our health outcome. And the question is there progression? Did they speed up their progression once they become CBD? Okay, so we're going to use just a mixed model for this, or a regular mixed model. and I have a random intercept for subjects right here. And we have those other terms. So here's our spline term here. And one thing you notice is I actually have a knot, but it's specific for each subject, because subjects may not progress at the same time, right? So this is one kind of added feature that I have is I'm allowing the time that they change to be subject specific. And I do that simply by allowing each subject to have their own knot. Okay, the time that they progress is going to be different. I do have an H here, so I actually could have added an H here on this side. Make that Hij. Okay, it's going to disappear on me. So, but you get the point. So here's our code. So what you do in your data step is you create that knot. Okay, so I have my regular data set, and now I just want to add this new term that will allow that change point. And so it's the max of time, that's our x variable, and CBDX, and that's subject specific. That'll allow each subject to have their own knot, at their own time point. So you just create that new term, and then you can run your mixed, and so you can see how it's not that complicated in terms of the amount of code that you have to write. It would be the same in R as well. So we have our time star, that's our term that's going to see if there's a change in direction of the progression. Then a progression group, random intercept. So this is just reflecting the model I wrote on the previous page. Here's some of the output that we get. So you can see, test for fixed effects, the covariance parameter estimates, and so forth. And then we get our parameter estimates and test for those. So, so what would you conclude by looking at this output? Again,
there's a significant.
Go ahead.
There's a significant change in slope at that progression point.
Yeah. So, and here I have it highlighted. I could have made it harder by not highlighting, but I highlighted it for you, but Lisa's right. So there's a significant change. And so that 1.528, that's our beta 2, right, from our initial model. So the initial relationship is here. So this is our beta 1 hat. Let's make sure that I'm using the same. Yeah, beta 1, beta 2. So there's a beta 1 hat, and then this is our beta 2 hat there. So the actual total slope is going to be that sum, but the change from the initial slope is the 1.528, and it's significant. So the progression becomes worse once they are diagnosed with CBD. Okay. Now here's the thing that we can do with our predicted values from this model. Because we have subject-specific knots, we can get predicted values that are subject-specific as well. So I have here 5 subjects just to illustrate this. And I know the graph is not that great, but it's kind of a default graph. So, so we have 2 subjects here of the same type, and then the 2 in red are the same. Those are the same types, and then the 1 in black. So what are the 2 blue lines, what do they relate to? What types of subjects are those?
people who never progressed.
Yeah. Yep, that's right. So these are the ones have not progressed yet. And maybe they won't. Maybe they'll stay just beryllium sensitized. So I'll put that, but we don't know. Maybe they won't. And this model allows us to, you know, we don't know. Maybe they will. Maybe they won't. It's not going to say they for sure will, but we know they haven't progressed yet. Whereas, what about this one, the black one, the top one?
Did that person progress before the study began?
Yeah, yep, exactly. So they progressed before the study. And then these two progressed during, and we can see their change points here, right? Here's the change point, and then here's the change point for the other subject. Pen is really fighting me today. And those, we need those subjects, those types of subjects, because otherwise we can't estimate the progression, right? It's those subjects that allow us to figure out the slope for the have not progressed and the progressed, right? So we need to have enough data where we're observing subjects during the study that change in order to get, you know, figure out what those slopes should be. Here's another data set. Any questions on that one?
I have a quick question.
Yeah.
So you're expecting progression in the positive direction. If it was in the negative direction, would you change the max to a min in your?
No, it's the same term, but it will automatically account for in the parameter estimate for your beta estimate. If your data is going down, it'll the beta will account for that. Okay. So yeah, really good question. You still do the max of x minus k and 0 as your term.
I have a question about what if you had data where you didn't have like a specific point where you wanted the knot to be? So like, could you use like something for the data kind of to determine where the change point would be?
That's a great question. Yeah, and that there's methods that are designed to figure out the number of points, the number of knots that you might have, and where they should be. Can you think of a way? How would you do it if you didn't have any specific method? Do you have any ideas about how would you approach it if you know, just based on what you know now?
I think it has to be something about the slopes, maybe.
Explain, what do you mean by that?
Like, if you're just looking at the, I don't know if it would be like with the regression line, but like, at what point, well, it would just be, never mind.
I think maybe are you saying that, you know, you have to look at the data?
Yeah.
Kind of plot the data and kind of visually see where there may be change points.
Yeah.
If that's what you're getting at, then yeah, that's one logical way. Like if you just want to understand the data and build a model for it and try to mimic the patterns, then you can just take a look at, look at a scatter plot and see what you have, and the data may suggest, where to place things, right? That's definitely one way to do it. What's a modeling approach that you might use? Like if you have, if you just have at one point, let's make it easy. There may be one knot in your data. What's a way that you can try to test to see, what's the optimal place for that?
Could you just look at like model fit statistics?
Yeah, you could. That's what you could do. You could like change the location, right? and then actually just get an AIC or negative 2 log likelihood if you're not changing the number of parameters, right? And compare those. And I think what you're going to find is that you're going to find kind of an optimal point. And in a lot of cases, if the data is easy, it's going to coincide with what you see, like what looks like is going to be the best point. But yeah, that's what you can do. You can take a look at the goodness of fit statistics and compare them as you change the knot location.
Okay.
So those are ways that you can do it, based on what you already know. But there's actually also methods out there that will tell you, here's where the knot should be. Like it'll search for them and kind of figure that out for you. And it may also indicate the number of knots that you would need as well. And there's actually Peter DeWitt, he graduated from our department, biostats. It's been a while now, maybe 4 or 5 years ago, and he did research in this area about where to play, how many to get and where to place them. And that's a big issue with spline modeling is, how many knots should I have? Where should I place them? What I'm talking about today, we're not focusing on that as much, but it's definitely a great question.
I have a quick question about the knot.
Question that comes up. Yeah, Jonathan?
Could you figure out the number of knots that you have in your data set by doing like a least centroids type of method, kind of like k-means clustering, where you can have like the distance between each centroid? Does that make sense what I'm trying to say?
I would need to, that's interesting. I would need to talk with you more about how to go about that. That's an interesting idea.
American Cancer Society has a program you can download called Join Point, and it will do that. I think you can look up to 5 knots or something, and it will tell you where to put them. And
really?
Mm-hmm.
Who is that? Let me write down what.
It's called Join Point. I think it's through American Cancer Society. It was developed for like time being your x-axis so that they could see differences in rates of cancer. So, I mean, it has some limitations, but it's pretty flexible in the grand scheme of things.
Okay. Yeah, so I think there's a lot of research that's been done in this area. Like spline models have been around for a long time, but this research to figure out optimal number and placement of knots, I think has been kind of relatively new, like it's been fairly hot within the last decade or so.
Can you also talk a little bit about the different types of splines, like the B splines or like the orthogonal ones?
Yeah, we're going to get into that later in these slides. I'll get into the B splines a little bit. So we have piecewise splines, there's B splines, there's natural B splines. And I'll get a little bit into that, not as much into the methods development, but the overall idea. So I'll present it and then we can talk about it more a little bit later in the lecture. So this other data set, Ed Hess was a student of mine maybe 12 years ago or so, and he works at the VA, so maybe some of you know him. He's an interesting guy because he actually wrote a book and published it, and a lot of that money paid for his graduate school. So I've talked to him a lot about how, publishing books and how he published books and so forth. So he, when he started working in the VA, he got this data set related to potassium. So basically, units of blood were sampled daily over the course of several weeks and assayed for potassium level. And what they did was they irradiated the samples. And what that did was it released free potassium. And so that raises concerns about, samples that if they're irradiated, it could lead to cardiac arrest. So they want to understand, they want to get a better understanding of the levels of potassium that change when they do irradiate the samples. So we're going to look at potassium level on the y-axis and then time on the x-axis. And we have a point where we know or we expect a change. So this is an example where we don't have to, we're not searching for the knot. We know where the knot's going to be. It's going to be when we irradiate the samples. And we expect a change in the relationship then between time and potassium level. There was a number of studies that were done. We're going to focus on this one where the knot is going to be at 7 days because that's when the irradiation happened of the samples. So here's what the data look like. Potassium levels naturally increase. Okay, they all start apparently around 10, and I don't know what the specific units are, but that's a relative amount of potassium that we have. And we have a natural increase, and then at day 7, after a week, those samples are irradiated. And you can see there's a change in the relationship. Then there's a quicker release of potassium in the samples once those are irradiated. But then over time, it kind of tapers off. Okay. So any thoughts on modeling this data? Like what kind of terms we would need? In this case, if we try to join 2 lines, it wouldn't look so great. Maybe the first part would be okay, right? We have a straight line that's not straight. We have a straight line coming through there, and then that's still not very good, sorry. But you get the point. So something's changing. So this is hard to do. So it comes up here, and then if we try to fit a line through there, right, it's not going to work too well. So we're going to need some higher order terms in here. It kind of looks like a quadratic might work, right? Because we just see that curvature. So we'll try a quadratic. We'll also try a cubic here. But we take the same approach, that we add terms at this knot point. I'm actually going to show you, initially I'm going to do a cubic. So here's our initial model. We have a cubic here, and then so starting at day 7, these are going to kick in, these extra terms. So since I have a cubic model, I'm going to allow also up to cubic for that. And I actually have a random slope for time here. And usually when you have a random slope for time, you're going to want a random intercept. So if you don't, there needs to be good reason not to have that random intercept in there. Well, by definition, these were supposed to have the same amount of potassium at the starting point. And that's the justification. So we're going to have, we'll be able to estimate that point with beta naught, right? But we assume that's in common to all subjects. Again, though, I just want to make the point that normally, if you have a higher order term, you have the lower order term, unless there's specific reason to exclude it. So in this case, there's enough justification not to have the random intercept in there. But we're allowing, samples that may tend to have a steeper potassium versus time relationship or a lower one. But we're only allowing linear deviations. You could also think about adding higher order terms for that. Okay. So we have our knot.
Do you have to?
Go ahead, Elise.
Do you have to have the same model on both sides? For instance, could I do linear on the first part and quadratic on the second?
You could. Yeah, you could.
Okay.
That's a good question. You could, we could add, it doesn't have to be constrained to be the same. I've done that here. You could play around with it a little bit, but I would say usually, if you have a third order function, usually you have that same order. We're going to talk in a little bit here in a second about when you want to drop the lower order terms and just keep that third level, or the cubic term in there, and how that impacts the function. But you don't have to, yeah, there's some flexibility depending on your data and the model you want to write. You could have them specified a little bit differently. So again, we have a data step where we create the S1, S2, S3 terms. And then we put them into our mixed model. And here's the output. You can see that the data are pretty highly correlated. Our correlation coefficient is close to 0.9, so that indicates a pretty strong correlation in the responses over time. Here's the test for each of the parameters in the model. And a solution for the random effects. So these are the linear deviations for the 6 samples that we have. And there's one in particular that seems to have a stronger, it's a negative, right? It has a lower potassium versus time relationship compared to the other ones, and is significant. So again, here's the subject data, and this is just looking up through day 15. And here's the cubic model, right? So looking at that, the actual data versus the predicted values, again, it's like taking a comb and putting a comb through it and straightening it out, to get the predicted values. I can't do that with my hair anymore. There's not enough of it left.
Question.
Yeah.
Quick question.
Go ahead, Jonathan, you're first, and then Benjamin.
Okay. If you test multiple of these knots, would these models be nested so that if you use the maximum likelihood, you could use the likelihood ratio test?
Yeah, you could do that. Yeah, you could do that test. Yeah, if you compare like the cubic to the quadratic.
Right, but I'm saying if you have, so your knot here is at 7. If you have if you run multiple knots in different models, are they nested? So if you fit another model with a knot at 5, would these 2 models be nested?
I think so.
Okay.
Yeah, if you keep the same knot at 7 and then you add some more knots in there, they could be
comparing 2 knots. So one model has a knot at 7 and the other has a knot at 5.
Mm-hmm.
So there isn't a 7 in both knots.
There is?
There isn't.
So tell me again, you have a knot at 7.
And so you have one model with a knot at 7, and then you have another model, a different model with a knot at 5, and you want to compare the fit.
I would just compare it with the AIC, like you have the same number of parameters, and then I would just look at the AIC or the -2 log likelihood.
Okay.
If it's the same number of parameters, you could just -2 log likelihood and just do a straight comparison of the whatever that gives you.
Okay.
And I think what you're going to see, like in this case, we knew where it should be, right? So I think what you're going to see is you're going to see like if you have AIC and then you have knot location on the x-axis, it's going to be like a U shape, and there should be an optimum, and it's in our case we know where it should be. But in cases where you don't know where it is, you probably see the same thing where there's an optimal point, and then if you go too far to the right, it's the -2 log likelihood starts going up. If you go too far to the left, the same thing.
Okay.
Benjamin.
Yeah, like 2 slides up where you had a data step somewhere.
This one?
Yeah, that one, this one. Yeah, so where you have if day is less than 16, and then the S1. So are we going to have some blank observations, and how are we going to interpret those areas with blank? Like S1 is starting somewhere, so
Yeah, so
like if you
it's not blank, it's actually 0. So that,
okay.
so like if you look over the times, you know, it'll be like 0, 0, 0, 0, and then all of a sudden it'll start taking positive values. So as opposed to like
Okay.
existing data. Yeah, so it's an actual 0 in there.
Okay.
Okay. Yeah, good question. So we compare these two. You notice that the predictive values are tighter here. Does that make sense based on what we learned before? Why might you expect that for these predictive values? Do you remember what we talked about before predictive values? These are these type of predictive values, right? And the B, what methods do we use to estimate those? Do you remember that?
Bayesian.
Yeah, Bayesian methods. And what Bayesian methods do is you can consider them as a weighted average of population information and subject specific information. And so what happens, predictive values tend to shrink back to the mean to some degree. Okay, the stronger the subject data is, the less that they will shrink back, but there will be some. And so you see some shrinkage back to the middle or the overall mean. And so that's why I didn't show that. I wanted you to answer that first. But that's not surprising because these predicted values incorporate Bayesian estimates, right? So again, mixed models, they use both. They use both frequentist methods and Bayesian methods. Okay, we use frequentist methods to estimate the fixed effects, and we use Bayesian methods to estimate the random effects. Okay, so here's the cubic model. Now, if we do the quadratic model, here's what we get. And what's interesting is this model has a worse fit. Even though if we look at the actual data, it seemed like maybe quadratic would be okay here. But what seems to be happening, and this happens a lot, is that it's more constrained. So it reaches a top, but it's actually starting to come back down a little bit because of that constraint. And the reason why the cubic works is because it allows sort of that flattening that we see at the end there. So even though we don't see a strong cubic here, to get that sort of flattening, we need that cubic term in order to get a better fit. So the cubic model worked well. So we can do a test to see if there's a significant change at all with respect to any of the terms. So the null hypothesis would be the spline terms are not useful, you know, at least one of them or any of them. Yeah. Okay, so the null is that none of those terms are significant, and then the alternative is that at least one is important, right? And specifically, the null is that they're all 0. So these beta 4, beta 5, beta 6 are related to the spline, the S1, S2, and S3 terms. And so we can do an F-test for that very easily, and we can see that this is not surprising. That's a pretty big F value, close to 200, and you know, you can see it, right? You can see it in the data very consistently for all the samples. Same thing is happening, right? So it's not a surprise that that's at least one of those is significant, you know, expressing the change from the relationship before 7 days and then after 7 days. So the other thing you can do with this, if you just have straight lines, that the slope tells you, you know, the rate of change over time. But here we have polynomials. So how do we get the rate of change at a certain point? Well, you can just take the derivative, right? So if we take the derivative of the function and then put in the value, we can get the rate of change at a specific value. This is just using basic calculus, took the derivative of the function. And obviously the function looks a little different if we're talking about before 7 days and after 7 days. So we can get one to express the rate of changes for x less than 7, and then one for x at least 7. And I did this right before class, so there could be some errors in it. But use my trusty Excel here just to check. So use the fit equation, using the fitted equations, we find that the estimated rate of change at day 6, that's what this is, that is that was that 4 point, whatever it was on that. .06. 4.06. So how do I get that? Well, I go back to the, you know, these are the, so beta naught I actually didn't write on there. See if this will do for me. It's smart enough. Yep. So these are the estimates for those parameters. And then I just figured it out, plugged in the value of x. So if x is 6 or 8, I use those values. And so this would be the estimate here. I'll post this on Canvas so you can double check my work. There's a chance I made a mistake because I did it pretty quickly. But I looked at the rate of change based on the graph, and it looked pretty close. So if there was a mistake, it's probably not too big. So 15.8. So let's take a look real quick if those make sense. The 4 and roughly 16. So at day 6, you know, what's the daily increase around that point? It looks like about 4. That looks about right there. And then at day 8, so we're looking at a point here, and then we're looking at a point here, and so the rate of increase would be the slope there, and it looks like 16. You know, I always encourage people to eyeball, like, we use these complicated methods, but always go back to your graph and see if your results make sense. And so it looks like that looks correct. So there's about a 4-fold increase in the rate of change in irradiation. Okay. So what we can do, actually, we talked about, you know, adding the terms, the spline terms. I call them spline terms, even if we're doing piecewise regression, it's just a little bit easier. If we want a smooth function, essentially what you do is you drop the lower order terms. So if I wanted for this model fit for the potassium, you know, we wanted a hard change and we expected a hard change, but if we wanted to make it smooth, what we could have done is just drop these two, like the linear and the quadratic. If we drop those, then it's going to force smoothness at the knot. Okay, so when we go to spline modeling, typically you're going to use cubic splines because that you know, allows that flexibility. It's enough terms to give you the flexibility, but not too much to over parameterize the model. Usually cubic splines are what you use if you use spline modeling. So you have your initial cubic function here, and then you add in the knots and the extra cubic terms that will allow changes to the function to fit your data. So we're honestly, it still doesn't look too bad, right? In terms of a parametric function, that's a parametric function. But if we add a lot of knots in there, then it gets complicated, and especially trying to interpret the meaning of those, right? They're just basically, the beta parameters are then used to shape that function that's trying to mimic your data. Okay, so this example is mouse growth data, and I obtained this from Rob Weiss's data set. He's in the Department of Biostatistics at UCLA. I was actually at UCLA, this is many years ago, in the statistics department. So they have a biostatistics department, and they also have a separate statistics department. I didn't get to know Rob personally because I wasn't in his department, but I obtained this data. He did a lot of longitudinal modeling, and I got into longitudinal modeling after I left there. But here's just the observed data on the left. So this is the weight of the mice over time. So they're born here on the left side, and then they grow. You can see that there's it looks like kind of a stronger growth period. The numbers aren't great on here. Trying to see what that is. Is that a 10 or so? So 0, 10, 20 is my guess. So initially there's a lot of growth, and then it starts to taper off a little bit on the right. So this would be a good example of what we talked about earlier, where there's not a clear knot point, and you may be better off trying to find a method that tells you where the knot should be and maybe how many to place in there. But you can get a sense as well just by looking at the data. You can get an idea. You know, that maybe placing a knot in this area, and then maybe in this area. You get a sense by looking at the data that you probably aren't going to need more than 2 knots in your data, right? So you're not going to get much benefit by placing knots every, 2 or 3 days here. So for these data, actually, I did use 3. So I'd be curious though to know whether, so maybe there was actually one kind of on either side of this. So maybe over here and then over here we place another one. So actually, to me, like it looks like 2 possibly, but I actually use 3. That's something you could test, right? So we could place these 3 knots in there. We can go in and compare it to an approach where you have 2 knots, and maybe change the locations of those. I actually did the same thing here with these data. The mice are typically pretty homogeneous, and they're going to be born with about the same weight. this case, it may be a little harder to argue why you wouldn't want to include a random intercept. But I did just have, for this modeling approach, I just included the random slope for time to allow deviations, for the mice that grow a little bit bigger and those that grow a little bit less over time.
Hey Matt, I have a quick question.
Yeah.
If the mice are homogeneous, why would you fit a random intercept on the individual mouse?
Well, I didn't.
Oh, okay.
And that was my justification.
Oh,
Although
sorry.
my point is that, there may be you could test for it even if you wanted to, but that's exactly what the thinking I had is, they should be around the same. So I'm forcing them to have, in terms of predicted values, they're going to be the same at 0. You're just going to have the fixed intercept there, and I'm forcing them through the same point. You could maybe test to see if you should add it. Again, the same point. I wouldn't say in general to drop the lower order term just by significance, but it should be based on rationale as well. So the knots in this data were placed roughly at 3, 8, and 13 days. And so we have this knot here is going to be, and this whole term, that's for the roughly 3, and then this is the 8, and this is the 13. So we're going to have a piece of the model that kicks in at that time to allow flexibility. This is the other kind of wrinkle that you have. It's if you have a hard change point, it's easier to figure out where that should be. But if you have a smooth change point, it's not so obvious where you should place the knot. Okay? Because, even if you look at the graph, it's like, even by placing the knot a little bit before where it changes may adequately account for that change. So it's a little bit harder, and you may need some help from goodness of fit statistics to tell you exactly where that placement should be. But I think in this case, there was some trial and error. I don't know, this data set is an older data set. I don't know if they used goodness of fit or some kind of model selection strategy to tell that this is where they should be. But we ended up using these 3, or he did, and I mimicked that. So we have knots at those points, and that's going to allow the flexibility to model the data. So yeah, somebody have a question?
When you say hard change point, do you mean you just know where it's supposed to be, or do you mean including those lower order?
Yeah, but when you include the lower order terms, you're going to get a hard change point, which is going to be used like for the potassium data, or for our first example with the chronic beryllium disease. I think for a lot of data though, I think those are probably more rare. I think more often you're going to want a smooth function, and so you're probably going to drop the lower order terms. But my point was that it's easier to pick the knots when you're doing the piecewise regression compared to spline modeling. When it's smooth, it's a little bit harder to know exactly where to place those knots.
Let's say if in your data you had like up until 3, it looked flat. Could you do something in your model to basically you don't want to have an effect up until 3?
I think you could, but I think there's some difficulty. That's an excellent question. Like even the potassium data suggested that maybe a straight line would be good initially, and you could try to, again, for piecewise regression, it's not as big of an issue. But when you start doing smoothing splines, I think that if you tried to drop the lower or the higher order terms early, that might have an impact on what happens at and after the knot as well. So you have to keep that impact in mind, as well as just what you're modeling on the early part, because it's all connected and you want it to be smooth.
Mm-hmm.
So I think that's probably a lot of the reason why you might want to keep those higher order terms early. But from a technical standpoint, I think you're right. There could be cases where you could, theoretically, yeah, you could drop the higher order terms and only have them kick in later. But I think it may be harder than you think to do that, I guess is my point.
Okay.
Because of the trying to consider modeling of the data together and keeping everything smooth. So what we end up for predictive values, because we didn't have random intercept, we're forcing everything through the same point when they're born. And we get, predictive values that look pretty good by adding those three spline terms. I guess my question would be, can we get a decent model fit maybe by just using 2 knots? That would be the thing I might test next here.
I have a quick question, Matt.
Yeah.
So the more knots that you add in your data set, how does that impact your estimates and your power to detect differences?
I think it's like adding more predictors would be. Okay. You want to avoid over parameterizing the model, because then you have issues of decreased precision, collinearity. You want to have enough terms but not too many. So it's kind of the same issue we face in trying to figure out the best number of predictors to include. Mm-hmm. So you definitely want to be cautious. You want to just throw too many in. And what's the other problem? If you add in a lot more knots, then you're going to start modeling noise, right? And so you can think of the global temperature data as well. Like if you're going to use spline terms there, if you add too many in, your function's going to have a lot of turns to it, and you're going to start modeling things that aren't really, that really shouldn't be in the mean process. They should be part of the error process. It's a good question. And it relates to our general goal in statistics is to have a sufficient number of parameters to build a model, but not too many. And that's our general goal that we're going to have in most all modeling that we do.
Have a knob for every point. Is that similar to like Kaplan-Meier?
Like this model fitting?
Yeah, if we have a knob for every point.
So Kaplan-Meier, Kaplan-Meier is a non-parametric technique as well, but that one doesn't require any knot placement, right? You're just allowing the data to give you a fit. So that's one of the things that, and that's a survival technique. But we're not forced to have any, figuring out number of knots and where they're going to be placed, like we do with spline modeling. That really shows you, I think, that spline modeling, honestly, to me, is more, I would call it semi-parametric. It's not really non-parametric, because we really are dealing with the parametric model. It's just that we're making it very complex. So let me get to really quickly. This is actually not right. The birth weight, not zero. They're not born with no weight. There's some weight to them. There's some positive weight, weight. But I do think mice tend to be homogeneous, so it's going to be pretty consistent about how much that is. Made some comments there. So the last data set I want to present to you guys, this is where we really add a lot of knots, because we have a long time frame that we're going to look at, and this is a true spline modeling approach that I'm going to apply to the data. So I have 10 years of data. We're looking at hospital admission counts and comparing them to daily PM10. So this is coarse particulate matter in the air. So it's a type of air pollution. And so you think the Sandless Valley, you know, if some of you may have been to the sand dunes, you know, really neat areas. Sandless Valley is, it's a high, flat valley, and very beautiful. It's surrounded by mountains on different sides. On the east side, you have the Sangre de Cristo Mountains, and then at the base of that, the sand dunes. So in the Sandless Valley, there's a lot of sand, and in windstorms, the particles are going to get in the air. So that's one of the main things that contributes to what we call air pollution. So it's not air pollution like you see in the city, but it's just particulate that's suspended in the air based on, you know, wind that picks up. And it could also be from farming. They do farming in the valley, and so there could be particulate that gets in the air. And it's a concern for people in the valley that are breathing, especially vulnerable populations like people with asthma. And so in this case, we're not looking at individual subjects. We're actually just looking at total hospital admission counts for the valley. And so this is getting into like using count models like Poisson regression. And we talk about those methods more, but what I want to talk about today is the modeling of the mean hospital admission counts over time, and how we can do that with spline modeling. So in this case, if we look at the data, here's just the hospital admission counts, and these are averaged, I think, over maybe a week or something. And I'm actually in this case, I'm doing a lowest fit. So this is another non-parametric regression technique that doesn't require knots in placement or anything like that. It's just averaging the points with a stronger weight to those around it. And I'll talk more about lowest regression later. But essentially, like if the points start going high, the mean is going to follow that. It's going to follow the data. The higher the value of the smoothing parameter, the more smoothed out this is going to be. So again, you want to try to find an optimal value of the smoothing parameter that's sufficient, but not too much that you start modeling noise. So what do you notice in the data? This is about 10 years of data. You notice that the hospital admissions tend to peak about once a year, right? Especially early on. And then later, it's like every other year, right? But we have cycles here. And so if we're going to do spline modeling, then what would you do in this case? You would kind of, you see cycles. So that suggests right there, you know, about how many knots that may be useful. One of the other things, though, that I can tell you about this data, we are going to put in a seasonal fixed predictor, and essentially that's month of year. So we have day of week, we have month of year. So we actually are, that's one way of taking care of the yearly cycle, but to get an even more nuanced fit, if I put in a knot at about once a year, what cycle would that account for? Would that be yearly or every 2 years? Lisa, you were going to say something. I saw you. So if we think of, you know, a function like this, going up and down, and like this is, these are like a yearly cycle. So they hit a peak in the winter. And I think a lot of that's because of the flu season for these data is what's happening. But you notice that some years that there's off years in there, right? Maybe the flu hits harder one year, but not in another year. But how many knots do we need to add? Like if we're just going to be, let's say if we place a knot here and here, well, that's not what I want to do. I want to ask you first. So like, what are we doing when we add a knot? We're basically adding a change point, right?
Can you add a knot at the beginning and at the end of all of these?
I think I would do on the interior. So you start your regular function, and then you add something in, like not at the very beginning, but like at the next change point.
But in between two knots, wouldn't you just smooth everything out?
Would you or could you?
Could you?
You could. Yeah.
Is there a point when you're choosing these knots that you're eventually going to get to overfitting if you select too many knots? So is there an ideal way to kind of avoid that, but also give a good prediction?
Yeah, right. So that's, again, that's the thing. And that's part of the reason why I didn't like, okay, so let me get to, I know I asked you a question, but maybe it was a little bit confusing. Like if we put in, like if we put in, we basically want to put in a knot where there's a change, right? So then we would put one there, we put one there, we put one there. That would be putting a knot in every 6 months, right? What I ended up doing though was I ended up putting in knots at yearly cycles. So roughly here, and then maybe Jonathan, this is what you're talking about. So I put in knots and yearly cycles. We're not accounting for an extra change point, but I did have, part of the reason why I did that, there's two reasons. One was I see a 2-year cycle on this side, but I also have, I have month in the model, which also accounts for seasonal change. So that, Samantha, I think you asked us, like, that's part of the reason why I didn't do one every 6 months, because I felt like it would be overfitting by having a knot every 6 months and having this seasonal predictor in the model. So I ended up doing a knot every year. So that's really going to allow us to model a 2-year cycle in terms of the spline terms.
How does PM10 actually fit into that graph? Because isn't it just date and counts per admissions?
Yeah, so what we do, and I know we're kind of getting towards the end here, so I'm going to have to just kind of wrap things up, but that's a really good question to end on. So first of all, let me just show you this. This is fixing the other predictors in the model, including the month, right? And including all the other predictors, and including the pollutant and so forth. And what do you notice by having the knots at every year? We're addressing the 2-year cycles when we add the cubic splines for time. Okay, and that makes sense because we added a knot in at year intervals. And so why do we do this, and how does it relate to the air pollution predictor? Well, what you want to do is you want to see what the association is between air pollution and health that is eliminating other factors associated with time, such as what's going to be accounted for here to a large extent. I mentioned it before, it's like seasonal flu, like 2-year flu, epidemics or whatever we want to call them. And we don't want that to be confounding our relationship between air pollution and health. So we just have one linear relationship between, we're assuming that there's a linear relationship between air pollution and health, but we want to tease out other factors associated with time. And we do that by having the spline terms and by adding in month, by adding in day of week, and the other predictors in the model.
What's happening to all the other information in between the 2-year smoothed out data? Are you losing that information?
No, you're not losing any. Like, are you talking about this function here?
Mm-hmm. Because you're smoothed out every 2 years, right?
Yeah, but we could now again we have months of year in the model. So if you incorporate that, you could see how that you'd have a yearly cycle when you add the spline plus the month of year term in there. I just didn't account for it here. I fixed this and I used December. This is for December, but you could actually kick that in and show that you have yearly things going on as well once you add that. So I'm not going to have time today to talk about the P splines versus the B splines versus natural B splines. So I'll have you guys read this. And I think probably what I'll do is when I come back to teach, which will be next Wednesday, a week from Wednesday, I'll just recap this and then highlight some of the things like involving the P splines and B splines, because I think it's worth 10 or 15 minutes. Have fun. Wednesday, I won't be able to do office hours, but Gary's going to teach anyway, and I don't think we'll have a homework. So I have another webinar I have to join on Wednesday. So if you guys have any questions, feel free to email me. Actually, I'll probably see you Wednesday because I need to record things. So I'll at least get started with you on Wednesday. Okay. All right. Have a good week, and just let me know. Email me if you need to.